All right, everybody, we are getting close to the end. Lecture 37, let's get started. Okay, so today what we're going to do is, today's going to be our last, what I'll call pure beam design lecture. We've got one topic left to discuss that's related to beams. Something that we've been sort of kicking the can down the road over the past few weeks, and we kind of need to just do it, so we're going to do that today, which is the discussion of shear. Now, as you all know, over the past couple weeks, we've seen that in most routine beam design problems, shear doesn't matter. You know, we'll have a situation where the shear load on the beam is something like, I don't know, 30 kips, but the beam on the flip side has the ability to withstand, I don't know, 200 kips. So we know that shear isn't really a problem. But there are situations where shear can be a problem. A couple of examples, one of them is bridges, where you're customizing the size of the girder and you're tailoring the thickness of the plates and whatnot, and so suddenly shear becomes a big deal. And there are a couple of applications in buildings, for example, transfer girders. So just to give you kind of an idea of what I mean by a transfer girder, so you all know, for example, if you have a frame, right, you've got beams, and columns, columns and whatnot. So imagine you have a situation where you've got, I don't know, a situation like that, where, for example, here's the ground, and you've got this one area in the building where you want to have something open. So a good example of that might be like a lobby in a hotel where, if you've ever been into like a really big hotel, you go into the lobby, you can see that it crosses multiple floors. That beam up there might have to support the weight of everything above it. So we call this a transfer girder, and that element right there has really high shears. And so being able to design for shear there is kind of important. As for housekeeping for the class, all the attendance is up to date, all the outstanding homework's graded. Homework 6.7 was due today. How'd that go? The high CB example. Hopefully it wasn't too many back and forth iterations on that. And I'm giving you a shear problem today. I will say one thing about the homework today and the homework that's, how can I put this, the homework is going to be due on Monday. One of the things that I have been maybe slightly guilty about this semester is I have sort of, for lack of a better term, spoon-fed the spec to you. And on this one, you're going to have to actually read the spec. I want you to actually open the spec and read it and digest how to compute shear capacity. Some of that we're going to cover today, but some of it we're not going to cover today, and you're going to have to read the spec on your own. But I'll get you started at least with that process today. Okay, everybody get the code? Okay. All right, so let's talk a little bit about shear. Okay. So I'm going to do a very brief coverage of shear, some of the mechanics and whatnot. This discussion is going to be sort of a refresher of what you discussed in Engineering 216. I imagine probably what Dr. Zatar for 216. So you discussed this there then, but unless you're actually talking about shear stresses, you probably don't actually use it very much. So I think it's worth rehashing, and then we'll get into the spec. Okay, so you have a beam, you take that beam and you apply force to it. Everybody here knows that you can develop from that a shear diagram and a moment diagram. Now, for, this whole time what we've been doing is we've been essentially drawing the shear diagram and moment diagram, and really what we've been doing is using a lot of shortcuts in the spec to calculate max shears and max moments, but everybody remembers this, right? But for the purposes of our design and what we've been doing for the past couple weeks, really all we've been focusing on is this. I mean, we do sort of a cursory discussion of the shears, and we find that, this shear is 30 kips, but the beam can hold up 200, and then we said, let's just move on. But we do need to recognize that flexural elements in general do have to withstand bending stresses, okay? Where do those stresses come from, though? Okay, so let's take a look at a very simple case to explain the point. Okay, so we have a beam, right? That beam is subjected to a point load in the middle, right? So we know that if this is 10 kips, then these two reactions are 5 kips. So So we go up 5, over, down 10, over, back up 5, right? Area of this goes up, area of that goes back down, okay? Now, the reason why I'm using this example is because I'm talking about shear, so I'm using about the simplest case that I can to illustrate an example of a constant shear, okay? Now, if we have constant shear, the question is, where do shear stresses inside the beam come from, okay? Well, they come from the change in moment, okay? So for example, if I look at some little element in the beam, if I just slice out some element and just look at that, okay? On either side of the element, we have a constant shear, but we do have a change in moment. Like we have a small moment over here, a little bit bigger moment over there, okay? So that's a change in stresses, and those stresses have to go somewhere. They don't just go away. The beam has to withstand that change in stress in some fashion, okay? And it develops internal transverse shears in order to ensure that the beam stays in equilibrium. So let's take that element, let's blow it up a little bit. So everybody in here should be familiar with this, right? So we have a beam, you know, this line right here, that's the neutral axis, right? So if you take a beam and you bend it, and let's say it looks like a big old smiley face, the top of the beam's in compression, the bottom of the beam's in tension, and that line in the middle doesn't really deform at all. We call that the neutral axis. Like it changes shape, but it doesn't get longer or shorter. And that's this sort of line through the middle right here. Everything above that line is in compression, everything below that line is in tension, okay? Now, like I said, if we go back, let's go back a slide just to make sure we can kind of see what's going on here. So I'm looking at either side of the element, so the left side of the element and the right side of the element. I propose that on either side of the element, we have a change in moment. We go from this moment to a little bit more, okay? So if we look at the bending stresses, we have the bending stresses, and then over here the bending stresses plus a little bit more, okay? That bending moment changes. So if we've got a little bit more stress on this side of the element than we do this side of the element, where does that stress go? Because if the beam doesn't have any way of resisting that stress, the beam's going to run away from us, right? Okay? Well, where I propose that beam develops those stresses is through transverse shear, okay? So a good example of transverse shear, you have a notebook on you, okay? So if you take this notebook, okay, this notebook is really, really bad at resisting transverse shear, because if I take the notebook and bend it, it's pretty easy to bend, right? Now, why is it easy to bend? It's easy to bend because this notebook has what? 100 some odd sheets in it, and these sheets are all sliding against one another. So, thank you. From a mechanics perspective, what I just did is I just bent 100 beams with really, really tiny moments of inertia. This essentially is kind of what I did, right? So now imagine, what if I wanted to play a prank on Mr. Pruitt, and I decided to get some glue and glue every single one of those sheets together and then try and bend it. Suddenly, that notebook gets a little bit more, it gains a lot more stiffness, right? Because the pages aren't sliding against one another. See, in between the fibers of, you know, the beam, we're developing these internal shear stresses, and that's where the equilibrium is maintained. That's where essentially the difference between bending moments on the left and bending moments on the right go, is those shear stresses in between the planes. There's nowhere else for them to go, okay? Does that make sense? That idea? Okay, now, does y'all remember this? It's probably been a while since you looked at it. Do you remember this from mechanics, right? Tau equals VQ over IB. Okay, so this is how we would compute those stresses, okay? And so I know it's been a while since you've looked at this equation, and that's okay. That's okay. We're just going to recap, okay? So tau equals VQ over IB. That's how we can compute how much shear stress is inside a flexural element. And it's a function of VQ over IB, okay? So what are those terms? What is V? That's the shear force, okay? So if we're looking at a given cross-section, V is going to be a constant, because whatever section we're evaluating, we cut a section, there's the shear, right? So the shear is 20 kips or 40 kips or 30 kilonewtons if we were doing metric. It doesn't matter, okay? But that's a constant value, okay? The moment of inertia, okay, that's also constant. That's the letter I. So VQ over IB. So at a given cross-section, V is going to be constant, I is going to be constant. What's going to be a variable, okay? Well, the first thing that's going to be a variable is this term Q. We use Q to represent the first moment of area. And basically that's just the area times the distance taken from the centroid. Okay? So what that basically means is as you go down the cross section, the shear stresses are going to change. Like for a rectangular cross section, the biggest shear stresses are in the middle, right? At the top and bottom, the shear stresses are 0. Okay? Because you're basically having area times the distance, but the area is 0. Okay? But B is the beam width. Okay? So the shear stresses inside a beam are a function of how wide it is. Okay? And this is kind of interesting. In a rectangular beam, that's a constant, but not in the case of an I-beam, like what we're talking about in here with steel design. So if you actually look at the bending stress profiles and the shear stress profiles, what happens is everybody should be familiar with this, sigma equals my over I. That's good, great, grand, and wonderful. Okay? But I propose that you get a really different profile in your shear stresses depending upon if you're looking at a rectangular beam like this or an I-beam like this. Now, we don't really look at this very much in steel design. We look at this in steel design. So what happens here? What happens here is, remember, B is that denominator, okay? And what happens from here? So we have a B, 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 boom. We have a sudden jump, a sudden change in B, okay? Because that's the width of the beam. So think about it like this. If the width from here to here suddenly gets smaller, it means this denominator suddenly gets smaller. And if the denominator suddenly gets smaller, the shear stresses suddenly get bigger, okay? Does that make sense? So if we were looking at a steel I shape and we were thinking about shear, where is the primary amount of shear carried in a steel I-beam? In the flanges or the web? In the web, right? Okay, the flanges, here and here, the flanges really aren't seeing hardly any shear stress. But the web, this part in the middle, that's what's seeing a lot of the shear stress. In fact, like a really simple way of thinking about it is if you're looking at an I-beam, it's the flanges that are responsible for really carrying the moment capacity, and it's the web that's responsible for carrying the shear capacity, right? So flanges sort of dictate how your beam behaves under moment. The web dictates how your beam behaves under shear. So I would imagine if we're going to start looking at shear capacity, we're going to focus on that, on the web. Okay? Does that make sense? All right, so now let's talk about shear. Okay? Let's talk about shear, and let's try and talk about shear as it relates to the specification. And so we're going to be focused on chapter G of the spec for today. So if you remember, so let's sort of have a spec review, right? So chapter D, that was the chapter on tension members. Chapter E, that was the chapter on columns. Chapter F, we've been in chapter F for a little while. Chapter F is the chapter on beams, but really it's the chapter on flexure, on bending. Chapter G is the chapter on shear. So we've been knocking this stuff out. Okay. Let's take a look at shear capacity. Whenever we're looking at shear capacity, we have to ask a question as to what limit states govern shear capacity. And either what's going to happen is we're either going to have the elements fail in yielding or the elements fail in buckling. Now, how would we, let's just think about this for a little bit. How would we figure out the maximum capacity according to shear yielding? Well, let's just think about this basically. I mean, how have we defined capacity checks really this entire semester? It's been some limiting stress times some limiting section property, right? So how did we do gross section yielding? A limiting stress of Fy, an area of Ag. What about plastic moment? Fy times Zx, right? So how do we do it for shear yielding? We take, what's the area? Well, the area is the area of the web, right? The depth times the thickness. What about the limiting stress? It's not Fy, it's 0.6 times Fy. Remember how I've said this whole semester, whenever you have something associated with shear, that 0.6 is going to pop up, okay? And is it a factor of safety? No, it is not a factor of safety. It is just a reflection of the fact that metals in shear do not resist stresses as well as metals in tension, okay? Does that make sense? All right, Now that is shear yielding. Let me talk a little bit about shear buckling, okay? So let me sort of show you this. I got a little link here. I'm actually going to pop this. So the other thing I'll say is that, so whenever you have a steel element and it fails at a 45-degree angle in shear and it buckles. But if you look at a concrete element, so if you look at concrete design, like here's a concrete beam, and you load it in shear, you get a crack that looks something like that. Because what happens is concrete is in compression this way, tension this way. Concrete does not like to be in tension, and concrete cracks when it's in tension. So when you load it this way, it cracks. So shear, 45 degrees, there's an analogy there. Okay, make sense? All right, let's talk about the spec. Now, I'm going to show a term to you. There's going to be some terms here in the spec that I want to illustrate for you. But I did want to describe what's going on here for a sec with these ideas of transverse stiffeners, because you're going to see this term pop up in the spec. So how many of you have been driving down the road and seen a steel beam with these plates like this? How many of you have seen that? Okay. I challenge you to start keeping your eye open a little bit. And one thing that's kind of interesting is keep your eye open for bridges that look older. Okay. Back in the 50s, 60s, even in the 70s, we were in a market where labor was sort of regarded, labor was cheap, but the material costs were very, very high. Material was expensive. So what we would do as engineers is we would try and shave every single pound of steel that we could off the girder. And so if you look at older bridges from the 50s and 60s and so on and so forth, you'll see stiffening plates all over the place, okay? Whereas more modern bridges today, like your regular old routine plate girder on a 120 foot bridge, you won't see many of these because we'll make the bridge 5 or 10% heavier if it means we can avoid these. We like to avoid these if we can. That doesn't mean we don't use them. Sometimes we have to, but again, we try and avoid them if we can. But if you see this term A here, this is the distance between stiffeners. So there's going to be spec that governs girders that don't have stiffeners and ones that do. And these are called transverse stiffeners because the beam's going this way and the stiffeners are that way. Okay. So yeah. Okay, so let's look at Chapter G, okay? So I want everybody to open their spec to Chapter G. Notice how, like, I've been teaching this class all semester, and usually what I'll do is throw these nice, pretty formatted equations on the slides. I'm not doing that today. I want you to actually open the spec, and I want you to sort of read things through. So we're going to do this today. So I kind of want everybody to have the spec available. But we're going to be looking through section G1 and section G2. And one of the things that's kind of interesting in the computation of shear, this is, I think, probably one of the only instances that we've had in this class where the value of phi is dependent. It's variable. In other words, phi might not always be a given value. Normally what we've been doing is here's a limit state, phi is 0.9 or phi is 0.75. In this case, phi can change, okay? And we've got this section G21, which we're going to look through here in a second. So I'm actually not going to say a whole lot about what's going on with the spec because I want you all to help me. Yes?
What page is chapter G?
We are on 16.1. I think it's 72.
Okay.
75. Dang it. All right. One thing I will say, though, just to give you a little bit of an explanation. So this is the only thing I'll say in terms of trying to explain the theory behind Chapter G. So essentially what we're going to do in Chapter G is we're going to calculate a base capacity, and then we're going to be adjusting it by this constant here. And this constant here is called CV, or CV1. The reason for CV1 is trying to account for the possibility of buckling. So if buckling's not going to happen, then CV equals 1. If CV is smaller than 1, it is reducing the capacity to account for the potential of shear buckling. Okay? But in terms of calculating it, you all are going to help me with the spec today. All right? I would pay attention to the spec, and also there are some handy user's notes trying to make your life a little bit easier. So we'll just leave you to that. And today, let's see if we can discuss a brief example. Okay, so what I want to do is I want to compute the shear capacity for a W24 by 62. Okay, we'll assume it's unstiffened. Bless you. That wouldn't really matter in this instance, and we'll see why here in a second. Now, notice for this problem, we could look it up. And what is the shear capacity for a W24 by 62? It is 306 kips. So let's see if we can calculate it, and let's see if we can get the same answer. Okay? So let's see what we can do here. Okay. So I do need some properties, by the way, for a W24 by 62. So let's list those out. Oh wait, wrong one. I meant to pull up my notebook. There we go. If I have a volunteer who's willing to turn away from Chapter G, I'm going to need D. I'm going to need the web thickness. And there's something else I'm going to need, which we haven't used yet. And this is going to be a fixed point of discussion on Monday, okay? Which is this term H over TW, okay? We have not used these yet. And this is new. This will be a point of discussion on Monday. Okay, so help me out. What's D? 23.7. Okay, remember, should be close to 24 because it's about how deep it is. The web thickness.
0.430.
And what's the H over TW?
50.1.
So this is what I'll refer to as a web slenderness. So, you know, we've talked about column slenderness before, and in column slenderness, we're looking at the slenderness of the entire column, the L over R. In this case, this is the slenderness of just the web, or the slenderness of just the flange. So we're going to talk about that on Monday, and we'll also kind of explain why the one for the flange isn't BF over TF, it's BF over 2TF. We'll explain that on Monday. Okay, so let's look at the shear capacity. Okay, so I have here, so I'm going to walk you through a little bit of it. So let's see what we can do here. Okay, let's start off with G1. Okay, so this is G1. Let's read this through. Okay, so what do we got here? The design shear strength and the allowable shear strength, so we're going to ignore all this allowable stuff because we're not dealing with AISC, shall be determined as follows. Okay, so that's what essentially is going on in this chapter. Now let's read what this says. For all provisions in this chapter except section G21A, this is our phi value. Okay? And then what it says is, so phi V and Vn, this is the thing about phi V, and Vn shall be checked for all this other stuff. Okay? So let's start here. For all provisions in this chapter except section G21A, phi is 0.9. I don't know about you, but maybe we ought to look at section G21A. So let's look at G21A. Let's take a look at it. All right. Now I'm not going to scroll to it here on the screen because I want you to help me out. So somebody tell me, what do I need to do in section G21A? Somebody tell me.
Compare H over TW to 2.24 times the square root of E over Fy.
Okay. So now that you said that, now I'm going to scroll. I know, I'm dramatic. Okay. So here's G2, here's G21, and here's G21A, and we're in this part right here. And so it says, for webs of rolled I-shaped members with this, phi is 1. Okay. By the way, does this look a lot like a slenderness check we would do for columns, like, you know, L over R less than or equal to 4.71 square root of E over Fy? This whole idea of checking against a limit of square root of E over Fy times some constant, that is a fundamental thing that you do with stability and buckling. So you see that all over the place in the spec. Okay, so let's do this. H over TW is 50.1, and (2.24) times the square root of E over Fy. So that's 2.24 times the square root of what?
29,000 over 50.
Okay. Somebody want to help me out with that? Say it again. 53.9. A second? So here we've got H over TW 2.24 E over Fy rooted. That's the case. And if that's the case, what is phi v?
1.
1. Okay. It's like we're reading the spec and we're interpreting the spec. It's crazy, isn't it? All right, I love it. Okay, let's keep going. Wait a minute. Let's think about this. What does this say? Let's keep going. For webs of rolled I-shaped members with H over TW less than or equal to 2.24 square root over Fy, we have this is true and that is true. That might be relevant. Let's write that down too. Okay. Okay. Yeah. Do a red line. Okay. So far, so good? Now, by the way, remember those user's notes I told you about? Read the user's note below here. So, yes. All current ASTM A6 WS shapes except these meet the criteria for Fy equals 50 KSI. So what do we have? A W44 by 230. This. What sample are we looking at?
2462.
I don't see a W24 by 62 here, do I? It'd be wonderful though if for my homework assignment I did maybe, I don't know, a W30 by 90. Look at me doing things. By the way, yeah, that's your homework assignment. You gotta do a W30 by 90. It's like I'm making you do stuff. Okay. Make sense? Okay. Now, we're getting ahead of ourselves here because I don't want to go too far down the rabbit hole. Let's go back to the very beginning. Okay? Let's go back to the very beginning. So let's take section G1. Okay? So this whole chapter, I mean, let's just be clear. This whole chapter, I mean, what's the title of this chapter? Design of members for shear. This chapter addresses webs of singly or doubly symmetric sections subjected to shear in the plane of the web. This. Okay. So here's the organization of the chapter. Okay, so let's take a look at this. So this is the organization of the chapter. And so let's just sort of digest what's going on here. Okay? Let's look at everything past G2. Okay? Do we need to worry about this? Okay, what about G3? Do we need to worry about G3 for this problem? No, that's for angles and T-shapes. We're looking at a rolled W shape. What about G4 or G5? Nope, that's square tubes, circular tubes, rectangular tubes. You don't have to worry about that. What about G6? Okay, G6, doubly symmetric and singly symmetric members subjected to minor axis shear. Is this a doubly symmetric member? Yeah, it's W sections are doubly symmetric. Is it subjected to minor axis shear? No. Okay. Minor axis shear would be if I were taking this and flipping it on its side and loading it like this, okay? Now, would I ever do that? Would I ever literally take a W section and flip it over and do that? No. But do W sections get loaded this way in the real world? Yeah. 2 examples. Wind and earthquakes. So that is a situation where that would happen in the real world. We're not worrying about that here, but we could. Do we have to deal with G7? Beams and girders with web openings. Do we have a web opening here for this problem? No. But can you start to think why that's relevant for this chapter? If the shear capacity of a W section is a function of the web, and we drill a hole through the web, it might affect the shear capacity just a little bit, right? Okay, so does it make sense that we're restricting our behavior or our discussion to G1 and G2? Okay, so let's go back to G1. Let's just read that again, make sure we're clear. Okay, G1, general provisions. This applies to everything. Okay, for every section, phi is 0.9, except the ones that meet this. And we happen to be one of the ones that meet this, so we're going to use a phi value of 1. So let's go to G2. I-shaped members and channels. Okay, now we're rocking and rolling. Okay, this section addresses the determination of shear strength for I-shaped members and channels. Section G2.1 is applicable for webs with and without transverse stiffeners. Alternatively, sections G2 and G3 are permitted to be used for webs with transverse stiffeners. So I do want to talk a little bit about that so that we at least have an understanding of what these sections are. So we have G2.1, G2.2, G2.3. Okay, so let's zoom out a little bit and see what we got going on here. Okay, so G2.1, shear strength of webs. Keep going down. Then we have G2.2, it says shear strength of interior web panels with A over H less than or equal to 3, considering tension field action, and then ones with a different, within web panels, considering tension field action. So what is tension field action? Okay, I'm going to say a little bit about that. One thing I'll say for the purposes of the spec, if you look at all the sections with tension field action, you will see a CV2, right? And so we're dealing with CV1. So that's the spec's way of differentiating that. So we're not considering tension field action. So what is tension field action? Okay, do you remember that video I showed you of the plate buckling, the shear plate buckling? What if I told you that after it buckled, you could keep loading it, and it would actually still keep resisting load? What happens what happens is, let's take the image here on the board, right? So you load this, right? It buckles, and so you have this buckled zone right here. So this is sort of where the buckle is, okay? Well, if you keep loading it, what happens is this piece of steel, this section of steel right here, is actually being yanked on. So really what you have is a situation where you've got a member, 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 and it's almost like a truss. And you can treat the plate girder like a truss, and this little band of plate within that panel, which we call a tension field, can still resist load, okay? And so you have to do that in cases where you have really, really high shear if you want an optimal design, so we call it tension field action. Those are highly specific cases in steel design. We're not going to worry about that for routine beams and buildings, so we're not going to talk about it here. So we're just in shear strength of webs. Okay, so how do we calculate the shear strength of a web? So let's go to G2.1. The nominal shear strength of a web is that Vn equals 0.6 Fy AW CV1. Okay? So let's write that down here. Okay, so let's see if we can fill this in, okay? So 0.6 What is Fy?
50.
So just so we're clear, this right here is Fy. What is AW? The area of the web. And what is the area of the web? All we're talking about is that web plate. The depth times the thickness. And what was the depth again?
23.7 inches.
And the thickness, I think it was 0.43. So this is the depth times the thickness. And then the last thing is CV. What is CV1?
1.
1. So what is VN?
12.9.
What?
12.9.
It's 12.9?
3.
I'm getting a bigger number.
306. 305.7.
Yeah, I'm getting 305.7 kips. Was it a decimal?
I forgot to put in the 23.7 inches.
That'll do it. So this is VN. Okay, if we want to be formal, we need a phi VN. But what was phi in this case? 1. Boom. And by the way, what is what did table 3.2 list as the spec?
306.
306. So if we go back up here, 24 by 62, we're looking at that value right there, 306. Not too bad, right? Pretty straightforward. So what I want you to do, so by the way, what I want you to do on the homework assignment is I want you to compute the shear capacity for a W30 by 90. And notice how W30 by 90 is going to change things. The spec's going to be different for the W30 by 90. But I do want to point something out before you go. Let's go back to the manual. I want to show you something. Okay, so here's the W shapes, right? W30 by 90. Let's take a look at something. So here's the W30 by 90. What are we talking about? Shear? You may notice this. Now we've kind of been just sort of looking past this whole semester. Like these shapes that have these little footnotes. What are these? Well, let's scroll down. Shape does not meet the H over TW limit for shear in AISC specification G2.1a. It's almost like you all now know what that means. So can you imagine that there are similar meanings for this right here? Shape is slender for compression with Fy equals 50 KSI. Maybe that's what we're going to talk about on Monday. What that means. It's all coming together. All right. I'm giving you 4 minutes of your life back. I'm going to put the QR code up one more time. That's all I got, everybody. You all enjoy the rest of your weekend, which starts early today.
You watched it last weekend?